I'd like to thank EE380 for inviting me, and I'd like to thank you for showing up. Do interrupt with questions if you have any, when you have any. So, are you ready to learn about the hilarious subject of computability theory? See, people are giggling. It is hilarious. So, let's talk about this. An algorithm is a sequence of instructions executed by a computer. Now, today we think of a computer as a machine, but originally it was a person, the woman or the man who executed the algorithm. Now, algorithms go back to Euclid's Elements in classical Greece and eponymously to al-Khwarizmi in 9th century Persia. But it wasn't until the 20th century that we get formal definitions of algorithm. When 3 papers appear, Alonzo describing lambda calculus, Kurt Gödel describing recursive functions, and Alan Turing describing what we now call Turing machines, all within a year of each other, something already alluded to. It's like buses. You wait 2,000 years for a formal theory of computability, and then 3 come along at once. So why did this happen? At the turn of the 20th century, David Hilbert in Göttingen was one of the foremost experts on formal logic, which was just being formed, Boole having sort of begun the subject just a little bit earlier. And he had a goal. His goal was to put every single mathematician out of work because he wanted an algorithm. What this algorithm would do is it would decide, given any statement in mathematics expressed formally, whether it was true or false. So you wouldn't need mathematicians anymore. You would just need computers that could execute your algorithm. And this was called the Entscheidungsproblem, because it sounds better in German. Now, Keats famously said, "What is beautiful is true, and true beautiful." And Hilbert figured the Entscheidungsproblem was solvable because he believed something similar, that logic was sound and complete. That is, what is provable is true, and what is true is provable. But in fact, at one of the talks at which Hilbert put forward this idea, we will know, we must know, the day before, this guy had proved that logic was incomplete, which means that Hilbert was, to use a technical term, screwed. Right? So what Gödel did is he had this incompleteness theorem in which he showed that he wrote out how you would go about expressing formally the definition of this is provable, and then he wrote a formal statement that means this statement is not provable. Oi. Right? As soon as you can write that down, you're in trouble. Right? This statement is not provable. So what happens? So if it's provable, then, if it's true, then it must not be provable. So there's something true that's not provable, right? The other way around, right? If it's false, then it is provable and you can prove something that's false. Now, that would be really, really bad news. That would be unsound, right? That kind of belies the whole point of having proof, right? The point is you prove it and it's true. So hopefully that option doesn't hold, but then you're left with the other option, which means it's true, and that means there must be something true that's not provable, which is not as bad as being unsound, but it's still really annoying, especially if you're Hilbert. Now, as long as people thought the Entscheidungsproblem was solvable, you didn't really need any kind of formal definition of algorithm. It would be just like Justice Stewart's definition of pornography. I know it when I see it. You just write out your algorithm. Yeah, that's an algorithm. But if you want to prove there's no algorithm, then you really need some formal way of understanding what an algorithm is. So the race was on. So the first horse past the finish line was Alonzo Church. And he came up with a definition of what it meant for something to be an algorithm. So he said anything you can write down in Lambda calculus is an algorithm. And he had certain ways of representing numbers in this thing called Lambda calculus and doing stuff with them. And then he showed that indeed that the Entscheidungs problem was not solvable if Lambda calculus was your definition of algorithm. Now, Lambda calculus, as we'll talk about a bit later, went on to become the foundation for functional programming. And I'm a functional programmer. And as was mentioned, this is sort of a theoretical talk. And the main reason for that is that people in industry have been ignoring what me and my colleagues have done for years and years and years. Right? But recently, of course, lambdas have become, here's your definition of lambda calculus, right? It's the world's coolest programming language because it was defined before there were machines that were computers. And of course, it's the world's shortest. It only has 3 constructs: variables, lambda abstraction, and function application. Okay. And as I said, people in industry have ignored it for years. But all of a sudden, right, this has become trendy. And languages like Java and C++ and Python all say, we've got lambdas, right? And there's Duke, the icon for Java, looking rather smug. Well, congratulations, Duke. You've managed to catch up with where Church was in the 1930s. So Kurt Gödel, remember him, was visiting at Princeton at the time that Church came up with all this. And he had a word for Church's solution. It was thorough. Well, actually he had 2 words: thoroughly unsatisfactory. So Church said, look, you come up with your own definition, and I will show you that mine is as good as yours. So Gödel did that. He came up with recursive functions. It was written down by Church's student Kleene with attribution. And indeed, Church and Kleene went off, and they proved that what recursive functions could do, lambda expressions could do, and vice versa. So they were exactly equivalent. And they went back, Church went back very triumphant to Gödel, said, look, they're exactly equivalent. And Gödel's response was to say, oh, my definition is the same as your official definition. Mine must be wrong then. Things stood at an impasse, and the impasse was resolved by this young man, Alan Turing, who came up with the 3rd definition, what we now call Turing machines. And what Turing did that was most important, that was different, was not mathematics, but philosophy. He explained why what a Turing machine could do would be the same as what a computer could do, where computer meant a person following an algorithm. So he gave a detailed argument with things in it explaining like, well, you must only be able to see a finite number of symbols at one time because people cannot distinguish between 999, 999, 999, 999, and 999, 999, 999, 999. What a lovely argument. So he made this argument, and that finally convinced Gödel, and all 3 were proved equivalent, and Gödel finally said, okay, maybe I had the right definition after all. Now, philosophers argue about whether ideas in mathematics are invented or discovered. But one of the themes of this talk is going to be when you have several things independently coming together, that's powerful evidence that you have discovered something. Gödel was 28 when he undid the work of Hilbert, who was at the time 68. Turing was 23 when he resolved the impasse between Church, who was 33, and Gödel, who was by then an ancient 30. So all you young people in the audience, you know what to do. Right? It's your job to keep explaining to your elders when we've got it wrong. Okay, so that's the background. And now I'm going to go on to explain propositions as types. I'll just pause for a moment. Are there any questions yet? Okay, you're not doing your job, right? You young people, your other job is to ask some questions. So you don't understand something.
Lambda calculus and functional programming.
Can I tell you why industry has ignored functional programming? That's a very good question. Let me go through the second part, which touches on that a little bit, or at least on what functional programming is a little bit, and we might come back to that at the end. But the short answer is no.
I got one. I don't know. I learned recently that Turing was doing some neural nets back then. I don't know if it was in the 30s or if that was maybe later than the 40s. But maybe they were considering like various other models of computation. I don't know. Were there any others that were sort of in the running?
Wait, 3's not enough for you that turned out to be equivalent?
No, 3's not enough. That would indicate that was the only one. What else did they think of?
Pretty much all the interesting models of computation are equivalent to Turing's and are equivalent to Church's. I think there are other reasons why people were not keen on lambda calculus. Kleene certainly talked about the reception for lambda calculus, even among mathematicians, being rather poor. So he switched to recursive functions. He said people like that a lot better. Certainly, Church did not do as good a job of explaining why lambda expressions did what they should do as Turing did of explaining why Turing machines did what was intended. But I'll return to that later. It's a good question. Okay, so let's talk about propositions as types. So we're still stuck in the 1930s. And this guy, Gerhard Gentzen, who was a Nazi, but fortunately that's not part of our story. We're going to talk about his mathematics. He, in what was essentially his doctoral thesis, so here's another lesson for you young people, right? This was his doctoral thesis, and in it he introduced natural deduction, the main system of logic that we use to this day. He also introduced sequent calculus, the second most used system of logic used to this day, and also, although quantification was already known and upside down E for existentials was known, he introduced the use of the upside down A to mean for all. So there's a goal for your PhD theses. And his key insight was that the rules of logic should come in pairs. So his logic was equivalent to earlier logic, such as Hilbert's, but he reformulated in terms of introduction and elimination pairs. And so that's actually from his paper. And if you look at these rules for and these rules for implication, I've just rewritten them here in modern notation. And you can see that the modern notation is exactly identical to what we have here for and implies, except I've written my letters, well, Gentzen wrote his letters in German, and I've written mine in English. So how many people here are familiar with these rules? Okay, fair sampling, but not everybody. So this is beautiful stuff and very widely used, right? Every database that you use relies on this theory, just to name one system that relies on this theory. Another system that relied on this theory is the Enigma machine that Turing built during the war, drew heavily on ideas about implication and formal logic. So if it weren't for these ideas, we'd all be speaking German right now. Ironic, I guess, given Gentzen's tendencies. So what did he do? Right? He said, okay, what does it mean to say A implies B? It means if you assume A, if from the assumption A you can prove B. And these little brackets around A say, well, I don't have a proof of A, I'm just assuming A is true. And that's superscripted with an X, and the X here means that this proof rule discharges the assumption. So we have a bunch of proof rules. So another proof rule says if you have a proof that A implies B, and you have a proof of A, then you can conclude B. And this is called an introduction rule because as you move down the proof, you introduce an imply symbol. This is called an elimination rule because as you move down the proof, you get rid of an imply symbol. And the way to think about it is this is all the stuff you can do once you know about implication. And this is what you need to know you can believe that an implication holds. So similarly, for conjunction, if you have a proof of A and a proof of B, guess what? You've proved A and B. And if you have a proof of A and B, what can you do with it? Well, there are two things you can do. One is you can conclude A, and the other you can do is conclude B. And then we can take these proofs and organize them into trees. So here's a very simple example. Here's the proof that B and A implies A and B. Are there any questions yet? Because I'd expect somebody at this point to say, B and A implies A and B. Come on, that's completely obvious. Well, yes, it is completely obvious, but it's not one of the proof rules I gave you. So if the proof rules work, we should be able to prove it, right? So how do you prove it? Well, to prove an implication, assume B and A. So there's the assumption of B and A. Then having assumed B and A, I can conclude A, right? Having assumed B and A, I can conclude B. Oh, now I've got proofs of A and B. So I've proved A and B. And now I can discharge my assumption. And now I know that B and A implies A and B. So the proofs just fit in little trees like this. I hope that gives you some sense of how discharge of assumption works. And if that all seems really simple, good. It is. That's the whole point. Okay, any questions about that? Now, the other thing you can do with proofs is simplify them. So this proof happens to be in simplest form, but we'll see an example of a proof not in simplest form in a minute. In fact, let me just move to that. So here's a proof not in simplest form. So here again, this is the proof we had before that B and A implies A and B. And here's some proof of B and A. So I'm not going to show you the proofs of B and A, but say there were some proofs of B and A. So here's my proof of B and A. And then from these two things, of course, I can conclude A and B, right? But this is a kind of roundabout proof because here I've just mentioned B and A, here I've mentioned A and B, here I've mentioned B and A, but here in the middle of the proof we've got an implies symbol. So Gensen wanted to know that whenever you did a proof, you only needed to rely on concepts that were in the hypothesis and in the conclusion. So we should be able to get rid of this other idea of implies, which isn't in our conclusion, and let's assume it's not in our hypotheses either. So can we get rid of this? Well, yeah, we can, because notice what this says is, well, assume B and A. Oh, but I don't need to assume B and A. I've got a proof of B and A right here. So let's just use that proof. So I'll replace the two assumptions by this proof. And now, right, and now I just get this proof of A and B. Okay, so I've just copied this twice to that place, and I don't need these last two rules. I've eliminated them. And now, notice I've got from B and A, conclude A, and from B and A, conclude B. But right, there's a much easier way of doing that, because just here I proved A, and just here I proved B, so I get a much simpler proof. So there's a direct proof from a proof of A and a proof of B. Of course, I can conclude A and B. So we've simplified the proof. So how did we simplify it? Well, we did two things. One is if we had an introduction, an implies introduction followed by an implies elimination, then what we did is the implies introduction assumes A, the elimination gives us a proof of A, just replace that assumption by the proof. Notice that, right, the assumption occurred twice, so we copied the proof twice. So we're making things simpler, but that doesn't mean we're making things smaller. We might be making things larger. Oops. And then the other thing, which is much simpler, right, says, well, if from A and B you've got a proof of A and B, and from that you can conclude A, hey, just use the proof of A directly. So those were the two things that we used in simplifying this proof. Question? Great.
I have, I guess, two questions, if that's okay. One is, so the little superscript letters and
Yep.
the brackets, we're just using those to tag different hypotheses, right?
Yes.
Okay. And I guess my next question would be, can we see the implication introduction rule again? I'm just wondering how we go from, I think I've seen something similar to this before, but normally presented with like a turnstile, where you can sort of say, oh, if you have these or I guess I'm wondering.
Right, so another way of writing this rule is, we have a whiteboard? Yeah. So what you're saying is you've seen the rule in a different form, and the form you've seen it says, if assuming gamma and assuming A, I can prove B, then assuming gamma alone, I can prove A implies B. Right, and yeah, more people tend to use this form much more often. This is actually called sequent notation. But still natural deduction proof. People use this form much more often. I like that one because I don't need to write, it uses less ink, basically. I don't need to write gamma every time. And this has gone out of favor, but I think it's actually much more compact.
Implication introduction rule, it's the same as that. It's just presented differently.
That's right. It's just two different notations for describing exactly the same thing. Good question. Thank you. Okay. So that was what Gensen did. And at around the same time, as I mentioned, Church introduced lambda calculus. Now, he didn't actually first come up with lambda calculus as a way of describing algorithms. He came up with it as a macro language for logic. And that turned out that it was so powerful as a macro language for logic, you could use it to write down essentially infinite formulas. And then using something called Curry's paradox, you could prove anything. So it was too powerful as a macro language. It made your proof system so powerful you could write down the equivalent of infinite formulas, and those would let you prove anything. So that wasn't very helpful for a logic. He already thought he was onto something, right? The first, do I have this here? No. The first paper that he wrote on lambda calculus, he actually said in it, it may be that it has uses other than just in describing a logic. And that turned out to be quite right. So lambda calculus, it turned out, was too powerful and made things inconsistent. But he could make things consistent again by having type lambda calculus. So the basic problem with lambda calculus, I'm not going to show this to you in detail, but the basic problem is you can write untyped lambda terms that don't terminate. And so you had formulas that had no normal form. Or there wasn't a formula there, and that was how you could prove things that shouldn't be provable. So if the proofs just would always terminate, if the simplification of the proofs would always terminate, you'd be okay. So he introduced what was called simply typed lambda calculus, and that turned out to make the system consistent because it turns out the terms in simply typed lambda calculus always terminate. So there you go, right? Turing shows the halting problem unsolvable. Introducing simple types makes it solvable. So obviously you're restricting your expressiveness a bit, but it turns out not very much. So let me show you the rules of simply typed lambda calculus. Let x be a variable of type A and n be a term of type B. Then lambda xn is a term that stands for a function with an argument of type A and a result of type B. So a simple example of this is A might be the type number, n might be the term x times x, which also has type number, and then lambda x times x is a function from a number to a number. It's the squaring function. Clear enough? Most of you have probably bumped into this by now, yeah? Just nod your heads if you're suitably bored. Or ask a question if you're confused. Okay. And then we can apply functions, right? So L is a function from A to B. And M is a term of type A. So we apply L to M. And we're applying a function that returns a B. So L applied to M, of course, has type B. And this just says that the actual argument matches up with the formal argument required by L. And we can also have a data structure. Let's have pairs. So if m is a term of type A and n is a term of type B, then mn is an AB pair. And if L is an AB pair, then first of L extracts the first component, whose type, of course, is A, and second of L extracts the second component, whose type, of course, is B. So let's try to write a simple program and see how type checking works. So here's lambda z, second of z, first of z. And this says, well, if z is a B A pair, then the result is an AB pair. So it's just the function that, given a pair, swaps its two elements. And how do we know this is type? We'll assume that z is a variable of that's a BA pair. Then second of z would be an A. And similarly, first of z would be a B. So second of z paired with first of z would be an AB pair. And then lambda z, second of z, first of z, would be a function from a BA pair to an AB pair. Clear enough? Right, Carl's completely bored because he knows this backwards and forwards. And let's just look at an example of a program. So here's this function that, that we just gave the type of. And let's apply it to some pair, let's call it yx, where y has type B and x has type A, so that'll be a BA pair. So now here's our function applied to yx, and we want to evaluate that. So you evaluate this using what's called the beta rule, which says you just take your actual argument and you substitute it for your formal argument. So we've done that here, and here where I wrote z, I've got my yx pair, and I've copied the whole proof that that pair is well typed. So now we have a proof that after we've done what's called a beta reduction, the result is still well typed. So now instead of second of z, first of z, I've got second of yx and first of yx. And of course, second of yx is going to simplify to x, and first of yx will simplify to y. And that's still well typed. We can just copy down the part of the proof that says, well, how do I know this is well typed? Well, because x has type A. So second of yx has type A. If we just replace that by x, it still has type A. And here. And similarly here, we've just simplified the proof. So now we've evaluated our program. So the swapping program applied to yx gives us xy. And as I mentioned, this process will always terminate. And the first proof of that was actually written down by Turing. Turing also wrote down the proof explaining that lambda calculus was equivalent to Turing machines. I mentioned that Turing machines were much more popular, and most people thought they were easier to understand. But if you read Turing's own paper on the equivalence between lambda calculus and Turing machines, pretty much the first thing he says in the first paragraph is, this proof is very useful because it means we can do everything, instead of using Turing machines, using, quote, the more elegant, unquote, lambda calculus. So Turing had good taste. And then these are just the rules for evaluating programs. So this just says, right, well, what is lambda xn applied to a term m? It's just n with all occurrences of x replaced by m. That's just the notation that means that. And then you can simplify the proof that the original is well typed to give you a proof that the result is well typed. And similarly for getting the first component of a pair. Now you're probably getting a sense of déjà vu. So at this point, I hope the organizers had prepared things as I asked, but could you reach under your seat? You should find there a pair of colored glasses. They should be rose-colored. You didn't do this? Okay, well, you have to imagine putting on your rose-colored glasses. And when you do so, of course, everything that's in red will go away. And what you'll see, of course, is that this, if you take away all the bits in red, looks exactly like this. And that everything we've seen, right, if you take away the red stuff, you get what we saw previously. So it's this exact correspondence, right, between what Gensen did and what Church did. Now, that wasn't actually recognized until quite a bit later. That's what's called the Curry-Howard isomorphism, which says that, well, functions are the same as implication. Product spaces are the same as conjunction. Also, it turns out that disjoint union, or variants, are the same as disjunction, and the empty type is the same as false. So that's a diagram due to Luca Cardelli, back from when he did type theory. So this was written up. So Haskell-Curry discovered something similar, but not exactly the same thing. And then this correspondence between Lambda calculus and natural deduction was written down by William Howard in Xerox notes that circulated in 1969 and didn't appear until this paper was published in 1980 in a Festschrift to Curry. So I bet everybody sitting here is going, wait a minute, that's completely obvious. Didn't they see that at the time? Well, no, we know they didn't see it at the time. The way that we know is, remember, I said that Gensen introduced two forms of logic, natural deduction and sequent calculus. He introduced sequent calculus in order to prove this idea that proofs are not roundabout, this idea that if you have hypotheses that mention some formulas and a conclusion that mentions some formula, you can always normalize your proof so that it only mentions your hypotheses and your conclusion and parts of those, the subformulas. So this is called the subformula principle. And he described this in his original paper, saying it's very important you can always do a proof that is not roundabout. That's the English translation of the word he used. I actually haven't looked up the German word. Does anybody know it? No, I have to look that up. But anyhow, he wanted to show that there were no roundabout proofs. But he didn't do it the way I just showed you. He did it by showing an equivalent to sequent calculus and showing that sequent calculus satisfies something called cut elimination, which is the equivalent of the normalization rules I showed you. And in that way, demonstrated the subformula property. Right, so it's irony time. Right? He needed a roundabout proof to show that there were no roundabout proofs. It wasn't until 1965 that Pravitz came up with the direct proof. And then shortly after that, in the 70s, this correspondence between natural deduction and simply type lambda calculus was discovered. So this is often called the Curry-Howard correspondence. Other people were involved as well. If you look at the work of the intuitionists, even before the 1930s, in the 1920s, they were saying similar things. They say implication is, what does it mean to prove that A implies B? It means you have a function that, given a proof of A, returns a proof of B. What does it mean to prove A and B? It means you have a pair of proofs, one of A, one of B. What does it mean to prove A or B? It means either you have a proof of A or you have a proof of B. And that's why they were in the intuitionists. They didn't accept that not A or A was provable, because they didn't know, you wouldn't have a proof of not A or a proof of A. You just had a proof of not A or A. So that's why they were called the intuitionists. So anyhow, lots of people say, well, Curry and Howard were great, but maybe some credit should go to Brouwer, Heiting, and Kolmogorov, the intuitionists. Some people say maybe credit should go to De Bruyne, who was the first person who actually wrote out a proof system and independently of Curry and Howard expressed these ideas. So propositions as types is a very handy name that distributes the credit equally. And that's why I started using that name instead. But you're free to use whichever name you want. Call it the BHK correspondence, call it the Curry-Howard correspondence, call it the Curry-Howard-De Bruyne correspondence, as some people do. So, yes?
Logic, i.e. does P and not P imply Q?
In classical logic, yes.
And also in intuition, it's the proof by contradiction.
Let's not go there just now.
Okay.
I'll say a little bit about classical logic in a moment.
Well, that's intuition.
Right. So the name for this is propositions as types. But we can see very importantly, it's not just about propositions as types. It's also, right, about proofs as programs. And even more than that, right, it's about normalization of proofs as evaluation of programs. One way of expressing all these ideas is in category theory. And it turns out that these are the type level of categories. This is the arrow level, and this is two-dimensional categories. We have arrows between arrows. So it's a fairly deep concept, right? And many people have said, right, it's not just the Curry-Howard bijection. It's the Curry-Howard isomorphism, right? It's not just that there's a one-to-one correspondence between these things, but there's a one-to-one correspondence between the structures that relate them, and a one-to-one correspondence between the structures that relate those. So that's why it's such a cool idea. Now, when I first saw this cool idea, I thought, that's cute. That's some kind of a coincidence. What I didn't think is, the standard scientist question, I wonder if this happens anywhere else. And what I certainly didn't think was, hey, I think this is going to be the basis for my research career. But that was kind of what happened. And the reason why is because it doesn't just happen for natural deduction and simply typed lambda calculus, but for pretty much, as was mentioned at the beginning, every single logical system you can name, there is a corresponding computational system. And I've mentioned just a few of those correspondences there. One of the interesting ones is that the classical intuitionistic embedding of Gödel corresponds to something called continuation passing style, which is a standard implementation technique. And this actually gives you an interpretation of classical logic. So if you have call with current continuation, which is an operation in some programming languages, you can use that to implement the proof of the law of the excluded middle. So it turns out classical logic falls under this. There are lots of different kinds of modal logics. One of those gives you monads, which is a very standard way of dealing with things like state and exceptions in functional languages. It's also used for dealing with concurrency in things like F#. One of my favorites is that, right, the fact that there's a correspondence between logic and computing means that we should expect that every good idea in computing has already been discovered by a logician. And indeed, this is what happens, right? So that when Milner came up with his type inference algorithm for the functional language ML, it turns out that had already been done by Hindley trying to understand certain aspects of logic. So the system is now called the Hindley-Milner system. And when Reynolds came up with polymorphic lambda calculus, which corresponds to generics in languages like Java, and indeed my knowledge of what Reynolds had done got fed in through the team to the design of generics for Java. It had already been discovered by the logician Girard, who had done an isomorphic system called System F. And now often this is called the Girard-Reynolds calculus. So what is Curry-Howard? It's a double-barreled name that predicts the existence of other double-barreled names, such as Hindley-Milner and Girard-Reynolds. So pretty much every functional language you can name has lambda calculus at its core. So this is kind of my invitation to you to go off and learn one of these languages. Now, all of these languages, so you've seen my argument here, right? This is a repetition of the earlier argument. I said 3 times people found the same thing. That means it's discovered, not invented. Twice independently, people find natural deduction and lambda calculus, and they turn out to be isomorphic. That's a discovery. And again, right, it doesn't just happen once, it happens lots of times. It happens for Hindley Milner, happens for Gerard Reynolds. Again and again, the same thing is discovered by different people. So I will not say there are not bits of these languages that are invented. They all have bits that are invented. But they have a core that is something that is discovered. Now, probably most of you use programming languages other than these. And those languages, many of them I would say, are not discovered. They are invented. And you can tell, can't you? Right. So this is my invitation to you to go off and learn a programming language that is discovered. Yes?
So the one language that I'm aware of that I don't see there is Bacchus's FP or his second attempt FL.
No. Bacchus's FP, yes. So that was a wonderful theoretical language. It was highly influential. It wasn't really implemented and widely used. I've given here a list of things that are implemented and widely used.
FL was implemented and distributed.
So this is a list of some functional languages, not a list of all. And you've just mentioned an important historical one that I've omitted.
So how did real languages like Java and C++, okay, escape from ideology and triumph?
So this is a repetition of the earlier question, right? How come we don't all use this stuff? I think the weight of this falls on the functional programming community. We didn't do a great enough job of explaining to other people how you can use this to do everything. Or maybe we're missing something. So the reason I'm here in the Bay Area is so I could attend CHI, right? I'm not really a human-computer interaction guy, but they had a workshop on programming language usability. And the idea is, let's do scientific experiments to empirically measure what people are more productive with, right? What is a better language design? And possibly from that, we can begin to work out scientifically whether or not functional languages are actually a good idea. So I think the fact that they are discovered rather than invented is powerful intuition or suggestion that they might be. But that doesn't save you from doing the experiments. You have to do the experiments. Now, you could say, well, wait a minute. Wouldn't it just be the case that whatever is more effective people would use? That was actually what I thought back in graduate school. In fact, back in graduate school, first I thought, let's do empirical measurements. And I found some papers people had written about doing empirical measurements about functional versus imperative languages. And they were all very consistent. Here was the consistency between them. If the introduction said, we think imperative languages are better, that's what the paper showed. If it said, we think functional languages are better, that's what the paper showed. So I thought, this is going to be hard. All right, let's just wait and see what languages people end up using. People end up using the better languages. I didn't really understand about network effects. Right? Network effects means that if something is popular, the next thing to become popular will be the thing that's like the first thing. And you can look at that and see, right, and that's why C begat Java and Java begat JavaScript. So one reason why it might be the case that things that aren't the best dominate could be things like network effects. Now, does that prove functional languages are better? Nope. We don't have that proof. I'm hoping that one outcome of this workshop, special interest group at CHI will be to begin the effort to find that out. And, it's very hard, right? I just mentioned that the first studies are really inconclusive. We're just beginning to amass some evidence for things that are much simpler than functional versus imperative. So this is a program that's going to take a long time. Right? But it's just like functional language, right? Functional languages used to be really slow. That's another reason people didn't use them. They used to not have good libraries. That's another reason people didn't use them. They used to not have debuggers. All you need to do is keep doing the same thing for 30 years, and you'll get a lot better at it. So I'm hoping we'll begin to do, and so these things which it used to be you couldn't practically use them, now you can practically use them, right? So one reason perhaps why they're not widely practically used is, well, it didn't used to be the case you could. Now it is, right? And you know this, of course, because you use Scala a lot. So wait and see if we can dominate over the network effects, wait and see if we can actually build up a body of research. And that'll be a long program. You know, the way to do anything is just start, go on, and keep at it for 30 years. So come back in 30 years when we might have an empirical answer as well. Yeah?
In traditional languages, people frequently confuse with better whether the language is better or actually whether the implementation is better.
Mm-hmm.
What's the equivalent in functional languages?
So the question was, people often confuse whether the language is better or the implementation is better. What's the equivalent for functional languages? And as I just mentioned, it used to be the case that implementations of functional languages were rather slow and used a lot of resource compared to imperative languages. That's not nearly as much the case now. So I think that's the equivalent of what you're asking about. So it used to be these things weren't very practical, but they're becoming more practical. And also, of course, functional languages often work better in the presence of concurrency because you're not trying to write, have many processes write on the same memory, which is a very difficult thing to analyze. So there's beginning to be much more interest in functional languages in industry for that reason. So let's just wait 30 years and see what happens. Yeah?
In the presentation of Lambda calculus that you gave, or like, when we were defining function application, we were textually substituting the value of the parameter inside the body of the function.
Right.
So that's, what is it? Pass by name semantics?
Call by name semantics,
Call by name
yes.
semantics. What sort of changes if you evaluate the argument first before you stuff it into?
So if you evaluate the argument first, it's called call by value.
Right.
And back when I first started to do this, there was a nice equational theory of call by name. There was not a nice equational theory of call by value. Now there are nice equational theories of both. In fact, I made some contribution to that. So you can just look those up and find theories for both. You can do it either way now. And in fact, right, call by name, of course, is horribly inefficient. What we do in languages like Haskell, which is call by need, is you make clever use of pointers so that you evaluate each shared subterm at most once. Yeah.
I have an empirical hypothesis that I think is going to be played out in the next 5 years. And that is that what the functional languages is in fact missing is concurrency. And that's going to be deadly as the number of cores goes up. We're just in the beginning. Right now, we get maybe 60. Once we get 100, 200 cores on a chip, then this thing's going to die.
So some of these languages like Erlang.
Functional languages will die. Erlang is not a purely functional language. Neither is Scala.
So there will be greater interest in languages that support concurrency as your theory.
That's right. That will be the only way to get performance.
So hold
That
on.
sounds
So you're saying the
miserable.
functional language? He said
Purely functional languages will die in 5 years because they won't be able to get performance.
which is opposite of what you're saying.
Not really, no. I think that the functional languages that will attract a lot of interest will be ones that support concurrency in one way or another.
But he's saying they won't be purely functional.
Why don't I finish the talk, and then we can have debates like that over dinner.
Here, because you don't need
Oh, right, okay, you're saying, wait, does concurrency fit into this? Well, that's my day job. It turns out, right, so I work on something, I have a large grant in the UK called a program grant shared with Glasgow and Imperial to look at something called session types, which are an approach to concurrency. And I got interested in that. I always knew concurrency was interested, but lots of people do concurrency. What can I contribute? Well, it turns out that Fenning and Karras discovered a correspondence between linear logic and session types. So I thought, right, I should be all over this because concurrency is really important. Oh, there are all sorts of problems with session types, yes, but it's a way into concurrency that has this logical foundation. Right, let me just wrap up. So there are lots of functional languages. By the way, the same techniques, since they can be used for proofs, can be used to represent proofs. So pretty much every proof assistant that you can name makes some use of these ideas as a way of representing proofs. And this comes up a lot in things like Coq, which has now been used for things like proving C compilers correct and proving operating systems correct or meet certain specifications. If you want to know more about this, there are many, many places to go. One place you can go is this paper published in Communications of the ACM in December of last year, and there are lots of other citations there if you want to look at other things. I'm certainly not going to claim this is the only or even necessarily the best place, but it might be a useful starting off point if you want to know more. So let me conclude. And since Turing's big contribution was philosophy, I'm going to conclude with a little bit of philosophy. What would happen if we tried to talk to aliens? So we've actually done this. This is a plaque on the Voyager spacecraft. Sorry, Pioneer, thank you. Thank you for the correction. Right, so this is trying to convey some information. Here's a map of where the sun is relative to various pulsars. The length of the line is the distance to the pulsar. It has little marks on it that you can barely see here, which are in binary the frequency of the pulsar. So this is explaining where the sun is. And then this bit here, so that's Pioneer in the background, and that's two people in the front, right? And they're now, would aliens understand this, right? So aliens could probably work out the notion of length. They could probably understand binary. What about this bit? Well, right, if Star Trek is correct, then the aliens will look at it and go, oh, they look just like us. Except they don't have pubic hair. But other than that, they look just like us. Or right, it might be the aliens are really very different and they can't perceive this at all and they don't really know what to make of this. Right. So some bits we can be pretty seems likely they'll be able to decipher. Other bits it's less clear. So what about Lambda calculus? What about extending programs to aliens? So Independence Day is a movie, and in it the aliens are destroyed by a computer virus. Here's a screen capture of the computer virus, and you can see that it's written in C. It's written in a dialect of C that only has open curly braces. So what are the chances, right, that you could give a computer virus to an alien computer in C? Probably not large. Probably aliens do not already program their computers in C. What is the probability? What if you sent aliens a program in lambda calculus? Now, they might well not understand the symbol lambda, right? But if you can do it in a way where they can just work out distinct symbols, they could probably work out how to parse it. They could probably work out, and I would claim it's quite likely that they would be able to decipher what lambda calculus is. If you sent them a program in C, maybe they could, maybe not. Sorry? With their virus checker catcher check. That's a different issue. But anyhow, making an analogy, right? I'd say lambda calculus is like this. They're likely to understand it. C, much less clear whether they would understand it or not. So does this mean we should call lambda calculus the universal programming language? Well, let's think about that for a minute. These days, actually, it's become common to talk about multiverses. This is from a play called Constellations. Normally, a play has complicated stage directions. The stage directions for this play are very simple. It says, when you're reading the play, a horizontal rule stands for a change of universe. So it's a play whose action takes place across many universes. Scientists make use of multiple universes, right? Things like the strong electron constant, it turns out its value, if it was much larger or much smaller, matter wouldn't cohere. So why is it that this constant happens to be just right for matter to cohere? Well, maybe there are lots of universes. Maybe in most of them matter doesn't cohere. We happen to be in one of the ones where matter does cohere because we're here to see it. So the fact that the universe can be observed might explain why those constants have the values they do, or in the range they are. So scientists actually make serious use of the idea of multiple universes. So what about lambda calculus? So I can imagine, right, different universes where gravity is different, or the strong electron constant is different. I at least find that easy to imagine. My imagination is not so good when it comes to imagining a universe where modus ponens doesn't hold. That's the law of arrow elimination, right? Where the basic rules of intuitionistic logic don't hold, aren't known, can't be talked about. I find it very difficult to imagine such a thing. Other people might have a better imagination, but I just can't imagine that. Right? So we can't, I'm sorry, I'd like to say lambda calculus is the universal language, but I can't. And the reason why is that calling lambda calculus universal is simply too limiting. So that's it. And I'll just to summarize the summary. What you should think is that if you have a hard problem to solve, maybe one involving multiple computers, then you should think that this is a job for lambda calculus. Thank you very much. So that's it, unless people have more questions.
We have one.
Yeah, I wouldn't expect any other questions in this audience. You guys are so shy.
No, I think, let me see, telling people no side effects is kind of extreme. I keep telling people I like this separation logic stuff where instead of saying none, you just have to describe what side effects you have. What do you think of that approach?
So several people have mentioned pure versus impure functional programming. I've not mentioned it. And one reason why is, remember, I mentioned that modal logic corresponds to these things called monads. And monads are a perfectly fine way of dealing with things like state and exceptions or even concurrency. So they're not necessarily the best way of dealing with concurrency. I would agree with that. But and linear logic then gives you a different way of doing it. And if you want to make the point, neither of those give your favorite way of dealing with massive concurrency, I would agree with that. And there might be other ways yet, right? What we've seen so far is that this is enormously productive.
Once you get 100
Let me
cores
finish
on
answering that
chips.
question before I answer your question. So, in fact, side effects can crop up using these approaches. Now, how does that compare with separation logic? So I kind of like separation logic. It comes from linear logic, so it has its roots in this body of work. So even if it turns out separation logic wins, I'm going to claim a win for theory. Separation logic is very much about banging on a single shared memory. And as Carl has pointed out, and as I mentioned, banging on a single shared memory is maybe not a good way to actually talk about very concurrent systems. So that's the one thing that I have against separation logic. It's fine for when you're talking about a single shared memory, but I don't think that works so well if you want to talk about very diverse concurrent systems. So we'll have to wait and see. But certainly there's a lot of interesting work happening in that area, and there will continue to be. And what the best way is to bring concurrency to the masses remains to be seen. But for very simple cases, functional languages work really well, as we all know, because MapReduce was inspired by ideas from functional languages.
Is there something analogous to session types for affine logic?
Oh, good question. Is there something analogous to session types for affine logic? And the answer is yes, it's called affine session types. And in fact, many of the people that do session types make them affine, and I sort of jump up and down and say, no, I think it's better for them to be linear, but both approaches work. I should mention the limitations for session types are about trying to give types that describe communication protocols. So session type, very simply, it might be this channel, I'm going to send a value of type A and then receive a value of type B, and then I'll send another value of type C. And then maybe I'll offer a choice between two protocols. And then, of course, on the other channel, right, if this channel is sending an A, this channel better receive an A. If this channel is receiving a B, this channel better send a B. If this channel is offering a choice between a C or a D, this channel better be making a choice between a C and a D. Turns out that that notion of duality corresponds exactly to duality between the connectives of linear logic. And so you can use this to express certain protocols, and the fact that it corresponds to a proof that normalizes guarantees great properties. You have no races. You're guaranteed to terminate. This is fantastic. Of course, it's also awful, because you're guaranteed to terminate and that there are no races. And sometimes you need a race. Sometimes you need something that runs forever. So how to extend session types to deal with those very important situations is an open question. So I would not want to say session types are the answer. I just think they're a very interesting approach because of this correspondence to linear logic. There are loads and loads and loads of approaches to concurrency. What's the right one? So if we can say, well, this one corresponds to logic in a certain way, that gives us perhaps a reason to believe it might be a good way to go. And just like, is Lambda calculus better than imperative programming? That has to be tested empirically. But it gives you a powerful imaginative boost in a certain direction. Carl.
In addition to the many cores, we have another problem, namely the Internet of Things, where we have a bazillion little local machines here in the neighborhood, each with its own local states, and functional programming doesn't work for that either. Purely functional programming. They send messages back and forth to each other. That's our new model of computation.
Purely functional programming works fine if you use a monad to represent the local state. Or there might be other ways of doing things as well. Sorry, wait. Sorry?
The monad linearizes everything. You have to pass the state along hippity hop, hippity hop. It's crazy.
Okay. Sorry, monads are no good because they're crazy. I'll take that back.
They're not crazy, they're just linear.
Many applications of monads are linear. The basic monad operations are linear. But there are other related structures called, Carl, just let me finish the sentence. There are other related structures called applicative structures, which are related to monads. It's a similar notion. Simon Marlowe, who works at Facebook, did a little DSL library based on the idea of monads and applicatives for doing filtering. Every time you look at a message on Facebook, that's been filtered by this software using the DSL that Simon Marlowe and his colleagues have written, and that's all written in Haskell using monads and applicatives. So at least sometimes this can be put to practical use.
That's true.
Yeah.
So I don't know anything about functional languages.
But you can learn.
Yeah. If I wanted to write a important real program and wanted to make sure that it was going to work correctly, and I'm willing to pay factors of 10 or something in performance, consider the software that runs your airplane or drives your car. Okay.
People are often not willing to pay a factor of 10 for those, but
Let's assume I am.
okay.
if I work in a functional environment, have I got a better chance of being able to prove it's going to work correctly?
Okay, so the question, I'll repeat the question, right? If you work in a functional language, do you have a better chance of proving properties of the software you're writing? The best way to evaluate that is to look at the different proofs people have done. And the answer is, if you look at something like the existing largest proof that an operating system meets its specification, the way they did that was they wrote the operating system in Haskell and then translated it from Haskell to C. But they did the proofs at the Haskell level. So there is at least some evidence that working in functional languages does indeed make it easier to prove various properties. If you look at the proof, sorry?
They proved that the translation was correct also?
This is the SEL4 work. You're familiar with that, aren't you?
Yeah, but I don't think they proved the translation piece correct.
No, they did. They proved properties of the actual code they generated. Right, but they structured it by writing a Haskell program. If you look at the proof of a C compiler that it's correct, done by Xavier Leroy and his colleagues, that was all done in Coq, and their model of what the compiler does is a functional language. So functional languages do have a good track record of helping people to structure these these proofs of real systems. I won't say you can't do it another way, but I guess I would say that the one case I know of proving an operating system and the one case I know of proving a realistic compiler were done with functional languages. Good question. Thank you.
But most programmers are dysfunctional. Because worse is better.
Well, I mean, this is certainly one of the issues with take-up of functional languages, which is training. People want to do what they know. And maybe not even unreasonably, they want to do what they know. And many people don't know functional languages. But that's something that an educational environment can help fix.
Yes.
So if you were going to teach programming to kids, what would you use as a language?
If I was going to teach programming to kids, what would I use as a language?
5 to 10-year-olds.
So to take slightly older kids, freshmen, we...
and unsullied. Away before they've learned JavaScript.
Give them Haskell.
Haskell? Maybe.
Anyhow, for freshmen at Edinburgh, we do teach Haskell first. There are many in the UK. Most places don't teach functional languages first, but Edinburgh, Cambridge, Oxford, Imperial all teach functional first. So that seems to work quite well. Now, for younger kids, the best place to look to see examples of that being done is Matthias Verleisen and the Racket crew are very keen on teaching programmers programming to high school kids. So they've got an environment called Dr. Racket. It's great for building games and so on. They have a purely functional style for building games in Racket. Racket's not a purely functional language, but they begin by teaching the purely functional subset of it to people in high school. I'm not sure they've gotten down to 5 or 10-year-olds yet. But I do think it's very important for teaching to people that young that you have good support for things like graphics and animation and so on. Functional languages can do a great job of dealing with that, but we don't have many systems that actually do it in a robust way that's good for handing to kids. Dr. Racket's one of the few. We need more of those so that we are a better choice for getting to people early. Otherwise, the fact that things like Scratch have such fantastic interaction and graphics might well dominate over the fact that they're not functional. So I agree the environment is very important as well, and we need better functional environments for teaching to young people.
Yeah, well, Scratch, of course, has other problems, but it's difficult to teach your young kids Scratch because their logic is not matched by the logic of the implementation of Scratch. They claim concurrency, but it's sequential, and that confuses kids. They believe the concern when it says it's concurrent it's concurrent. Okay, that's an interesting thing. I think that the concepts of programming actually are probably inclusive of functional programming, but somewhat larger in terms of scope.
I'm not going to claim that functional programming is all there is. I am going to claim that it's really interesting and very worthy of attention. Anybody other than Carl?
Do you think that you could implement Linux in a purely functional language?
Well, as I
The
said,
operating system.
SCL4, the one formally validated operating system, they began by writing Haskell programs.
Right. But that's a different question as to whether you think that in purely functional Haskell, you could implement Linux, i.e. the way it really works today.
What compatibility?
Well, since Linux really is the default operating system now and into the future, it's kind of important.
Yeah, but if it's not different, what's the point? If it's completely compatible, then why bother doing it
It's
again?
merely what the Internet of Things is going to run on. You can't dismiss that.
Yeah, but just why not run it on Linux?
It would indicate if functional programming can't do it, it would indicate a fundamental lack of power in functional programming. If it just really can't do it, then that's a limit.
Well, I think that's something you want to take offline.
Yes.
It's
That sounds like a
long and involved
fair
argument, not resolvable in class.
What time do you officially end?
We ended at 5:30.
Okay. We thank our speakers.
Although we do have the room until